In this video, we're going to introduce the one-way ANOVA. ANOVA is a new term that we haven't talked about before. It is actually called the analysis of variance. So ANOVA is short for analysis of variance. We're going to use this technique or this statistical tool where we have the following data. We're going to have two variables. One of the variables we can call a factor. So some people call this a one factor ANOVA, but we'll have one variable that's a factor, and that's a grouping variable that usually has more than two groups. And then the other variable is going to be a quantitative variable. So if you wanted to really and truly think about this, you're going to have a categorical variable, which is our factor, and a quantitative variable. And you're usually interested in the differences in the means of the quantitative variable for each group or each category that we have of that categorical variable. And so you can think of this as an extension of your independent samples t-test. Remember your independent samples t-test? We looked at a comparison of two population means. So we had two groups. Well, the one-way ANOVA, we're just going to have three or more groups. So let's look at this example as we introduce this new topic. It says, suppose that there are four different methods, and the methods are given by the letters A, B, C, and D. These are training methods for recruits to be firefighters. We randomly assign each of the 40 recruits to one of the four methods. So that means that there are going to be 10 recruits in each of those groups. At the end of the training program, we administer to the four groups a common test to measure understanding of firefighting techniques. Ultimately, the goal is to test to see if there is a significant difference in the mean test scores among the four groups. I want to identify the variables in this study, right? So we have the groups and then we have the test scores, right? So we have two variables, right? Our first variable is the training method, where we have those categories of A, B, C, and D. And our second variable is the test score. Notice here that I know a lot of times I've seen students confuse the number of groups to be the number of variables. That is not the case. Training method, which is the grouping variable, is one variable. There are just four values of that variable, right? But it's our categorical grouping variable. In experimental research, we call that an independent variable. So that's why you see the IV in abbreviations there in that parenthesis, but we can also just call it a factor, right? That's our grouping categorical variable. Our test score, of course, is a quantitative variable, and it's sometimes called the dependent variable in experimentation or experimental research. You can also call it the outcome, right? That's the stuff that we're going to be calculating the population means for. That's our outcomes of that study. All right. Now, you may be asking, oh, well, since we already know the independent samples t-test or the two sample t-test, why don't we just do a bunch of t-tests, and that will allow us to test hypotheses about comparing the means of the four groups? Well, and of course, with the two sample t-test, you're going to do them two at a time, right? So this question here asks, how many pairwise comparisons are there among those four groups, right? And that will be that will tell us the number of t-tests we would have to do if we were going to do a bunch of two sample t-tests, right? Well, since there are four groups, one of the comparisons would be between groups A and B, another between B and C, another between C and D. And we'd have to test all of the groups for comparisons because, of course, we're not going to have exactly equal things. And so we can go forward and compare A and C, B and D, and as well as A and D. And so that leaves us with 6 pairwise comparisons. And so if we only wanted to use the independent samples t-test, we would have to conduct 6 t-tests in order for us to draw conclusions about the study here. All right? But we actually should not do that. And I'll tell you why here. So remember when we set our significance level alpha in our before our study is even conducted, whenever we're doing a hypothesis test. A lot of times in educational research, we use alpha equals 0.05, right? So suppose we have alpha equals 0.05. That means our probability of a type 1 error is 5%, right? So I'm okay with 5% of the time yielding an error when I do a hypothesis test. That means 95% of the time I should make the correct decision, right? So the probability that we do not make a type 1 error is 1 minus that 5% or 95%. Well, back in this case with this specific problem, if we were going to do 6 t-tests or independent samples t-tests, then our probability of yielding a correct decision or making a correct decision or conclusion when we conduct those 6 tests, well, those 6 tests will be completely independent. And there's a rule in probability that the probability of events that are independent is just the product of those probabilities. So I can calculate the probability that all 6 of those t-test decisions are correct by multiplying 0.95 6 times, or you can say 0.95 to the 6th power. When I do that calculation, I get 0.735, which is the same thing as 73.5% approximately, right? And so if I wanted to now adjust my type 1 error and calculate the probability that at least one of those tests is incorrect, well, there's another rule in probability that says, oh, if I know the probability of something happening is a value, I can just subtract that probability from 1 and it'll give me the probability of that thing not happening. It's called the complement rule. So the probability that at least one of those t-tests is incorrect can be calculated by doing 1 minus the 0.735, which is a 26.5%. This 26.5% is called our family-wise error rate. And it is kind of like an adjusted type 1 error rate whenever we do multiple tests. And so although we may at the beginning of a study set our type 1 error rate as 0.05, if we were to do all of the multiple testing, all of the pairwise comparisons, our type 1 error rate is going to be much larger than that, which is this 26.5%. And we do not need that error to be that high. Otherwise, we're not going to be able to believe those results. This is why we don't use the independent samples t-test to analyze a data set like this. All right. So the one-way ANOVA is our option here, our solution for that. It tests differences between the multiple groups simultaneously with a single test, and it maintains or keeps that type 1 error rate at alpha, which is generally 0.05 for us in the social sciences. The null hypothesis is going to look very similar to the null hypothesis when we have a 2-sample t-test or independent samples t-test. But now we're going to start writing our null and alternative hypotheses in words instead of all of the symbols, because there's a lot more symbols here. And so a lot of times it's kind of easier to write it in words. So, but we're going to have a similar null, right? All of our population means are going to be equal. If you like to write it in symbols, you can write it this way. You're going to have H naught, mu1 equals mu2 equals mu3, all the way up till we get to mu sub k, where k is the number of groups. And so in that last example, we will stop at k equals 4 with the firefighter example. So you can write your null hypothesis either of these ways. The choice is yours, to be honest with you. Our alternative hypothesis, and actually before I get to my alternative hypothesis, I do want to make a note here. This is a compound hypothesis here. We're testing multiple statements here, not just that mu1 equals mu2, but also that mu2 equals mu3 and mu1 equals mu3, so on and so forth, right? So this is a compound null hypothesis. Usually when we have compound null hypotheses, our alternative hypotheses are not directional, all right? And so as you're going to see here, we're only going to have one type of alternative hypothesis, unlike what we saw with the 1-sample t-test and then the 2-sample t-test, as well as pair samples t-test. Because those alternative hypotheses are the nulls we're testing one independent statement, we had an option to choose our alternative in a directionality or non-directional way, right? Well, when we have these compound null hypotheses, we can't do that. All we can say in our alternative here is that at least one of those population means would be unequal. And in symbols, we can say it this way: at least one mu sub I is different, where I would be one of the numbers from 1 until you get to k. All right. All right, so you don't have to write your null hypothesis in two ways like you see here, and your alternative in two ways here. You can write it either way, and actually, you're going to see that I'm going to use some more terms even when I'm writing my null and my alternative hypothesis. All right. Now, notice that my population means are in my null and my alternative hypotheses. But the name is called the one-way ANOVA, and I said the ANOVA is the analysis of variance. So why is there a focus on variance when our goal is to compare the group means, right? Well, let's say that I had an example, and we can make this the example. This is not, I simulated the data on this page here, so it's not necessarily data from the firefighter example. But in this data set, these two data sets that I simulated, there are 4 groups, and we have a quantitative variable where the individuals within those 4 groups were measured, right? And so I want to talk about why we're analyzing variance without getting into the actual formulas that are used to conduct the actual ANOVA test. So this is more conceptual, and that's the way we kind of are going to go through this for this course here. Well, if you look at this first table or figure to the left, there is smaller within group variability. All right. That means if I go to each group and just look at them separately, so I'm going to this first group, how spread out are those observations within that group? That is what I'm talking about when I talk about within group variability. And if I look at this first figure here, all of the within groups variabilities are very kind of small, especially in comparison to the within group variability to the graph to the right, right? So we have smaller within group variability. That just means that each group has values that are tightly clustered together. It is smaller in the graph to the left and larger in the graph to the right. In the graph to the right, there's a lot more spread in those quantitative values that are given by this axis here in this group, in all of the groups to the right, in the graph to the right. But that's what I'm talking about when I'm talking about within group variability. There's another source of variability that's going to be very important when we talk about the one-way ANOVA and, a two-way ANOVA, which we're going to see later. And this called the between group variability. Now, I want to talk a little bit about between group variability because it actually is coming from the actual means of each group. If you look within each of these groups here, there's a horizontal line segment, and that horizontal line segment represents where that group mean would lie. So if I look at this first group in the graph to the left, the group mean for group 1 would be about 70, kind of halfway between 60 and 80. This one would be about 90 something, right? That would be, if I kind of track it back to that axis there, that'll be about 90 something. And then we see this is the group mean for group 3. This is the group mean for group 4. When I talk about between group variability, I'm talking about how these group means vary from one group to the next. That's why it's between groups. It's the variability of the means between this group, between that group, and that group. All right. In this graph to the left, it is a little bit easier to detect differences in these group means, the differences between those group means, as compared to detecting it in this graph to the right. Notice how the graph to the right has a larger within group variability. It's a little harder to see that in general, the individuals in group 1 are different than the individuals in group 2, right? Because there's a lot of overlap between those distribution, or the spread is so wide that there's a lot of overlap. it makes it harder to detect the differences in group performance when our within group variability is harder as compared is larger as compared to when it is smaller in this case here. And so what the ANOVA does is it takes both between group and within group variability into consideration when it's comparing means. And the means are actually appearing in that between group variability. All right. So this says that ANOVA determines if group means are significantly different by comparing the two sources of variability. The between group variability, which is about variance between group means. Are there differences between those group means? How much different are they? And it also takes the within group variability into consideration as well, because if you're looking within group, it's harder to say that one group is better than the other. If there's a lot of variability, there's a lot of overlap, you're going to be less likely to say that those groups are performing differently. All right. Now, the way that ANOVA takes both of these sources of variability into consideration is by looking at an F ratio. An F ratio is going to become our test statistic. And it's basically a ratio of the between group variability to the within group variability. So we need a measure or some number that represents the between group variability. And we're going to divide that by the within group variability, some number that represents that. When we do this ratio, first of all, it needs to be in the same units and all that stuff like that. But once we do that, if we end up with a value that is large, then we know, well, if this F is large, that means the number that's on top of the fraction in the numerator was large, right? So that means between group variability is larger than the within group variability. That provides evidence that at least one of our means are different. So at least one mean is different. We'll be more likely to reject our null hypothesis if that is the case. However, if our F statistic is close to 1, that means that between and within group variability are similar in size, and that's not going to provide us with much evidence to reject our null hypothesis, right? Which means that we're probably not going to be very likely to have means that differ. And so if I want to know the full one-way ANOVA F test, these once again are our null and our alternative hypotheses. Because we're not specifying which mean is necessarily different, sometimes we call this a global test because it's not specific enough to tell us which mean is different, right? But our test statistic for this test, right? We know we're going to have to gather our evidence. Our evidence comes by way of our sample information, and that is calculated based off of our test statistic. Well, our test statistic here is an F statistic, and it is just the ratio of the mean squares between groups to the mean squares within groups, right? In that last slide, I said we need some number that represents the between group variability. Well, the mean squares between groups represents that between group variability. And then we needed a number for our within group variability. So our mean squares within is that number that we use. Once we get our F statistic, we can go to what we call the F distribution. This is an example of an F distribution. Notice it is not symmetric. It is not bell-shaped. It is actually a unimodal, asymmetric, positively skewed distribution. All right. But it works kind of the same, a similar way when it comes to finding our p-value. What we'll do is we have to specify which F distribution. So just like the normal distribution was kind of specified by its or identified by its mean and its standard deviation, and the T distribution, it was kind of identified by its degrees of freedom. Well, and remember, degrees of freedom, mean, and standard deviations were called the parameters of the normal and the T distribution. Well, the parameters of the F distribution are the following. There are actually two of them. There's degrees of freedom between groups, which is k minus 1, or the number of groups minus 1. And then there's a And remember that degrees of freedom there is in the numerator, aligns with what's in the numerator of the F distribution. So some people call this the numerator degrees of freedom, the DF between. And then the second parameter is the degrees of freedom within groups, right? And notice within group information is in the denominator of that F statistic. So some folks call the degrees of freedom within the denominator degrees of freedom, since it's in the denominator of the fraction. All right. But that is equal to capital N minus 1, where that's your sample size minus 1, and that's your total sample size. So out of all of the groups all together, that'll be N minus, and I know I just said N minus 1, it's N minus K. So your total number of observations in your entire sample across all groups minus the number of groups. Once I know these two things, I know the appropriate shape to make this F distribution. And so once I plot my F distribution, my p-value is going to be as always, your p-value is the probability of that test statistic or one more extreme in the direction of the alternative. Well, with this distribution, our alternative is, since this is global, our alternative is non-directional. So we're not saying that one group is bigger than the other. We're not even pointing out which mean is different, right? So we kind of got to think about this one a little different. With this F distribution, when we get our p-value, we always look at this right tail of the F distribution. We never look at the left tail, because those are not F statistics that are more extreme than the one that we have in our obtained in our study. So every time I calculate a p-value, it's always going to be that upper tail probability, and that's because we only have one tail on this distribution. This is different from what we did with the one sample t-test and the two sample t-test, as well as the pair samples t-test, where it depended on our alternative as to whether we're going to look at the upper tail, lower tail, or both tails. Every single one-way ANOVA, we're looking at the upper tail probability. All right. Now, because we don't have directionality here, we don't have to specify anything about our alternative to make JAS give us the appropriate p-value. It is automatically always going to give us the appropriate p-value. All right, here are the assumptions of the one-way ANOVA. We need independence. So the individuals within each group are independent, and across the groups, they're independent. So like in that firefighter example, there's the individuals in the firefighter group A, method A, should not be related to B, C, or D, and all combinations. No one should be related, right? If that is the case, then we need to use some other method. We need normality, so our populations need to be normally distributed, and then we need the homogeneity of variance. Remember, that is that your groups have equal variance. One way that we tested that assumption is by doing Levene's test. If that test ended up being significant, meaning the p-value from that test was less than 0.05, we will resort to using Welch's ANOVA test. All right, so let's go back to that example where we had the 4 groups of training methods, and we gave the firefighters a test. We want to test if there's a significant difference in the mean test scores among the 4 groups. We're going to use an alpha of 0.05. Remember, I said that there's a couple ways that you can write your null hypothesis. I'm going to have 2 ways written on the screen. You only have to choose one of these. There are multiple ways, multiple words that you can use, but in a sense, your null hypothesis is going to be that all of the population means are equal. Your alternative hypothesis is that at least one is not equal, right? I'm just showing you another way that you can write your null and your alternative hypothesis here. Here, I have my null is that there is no significant difference in population mean test scores among the 4 training methods, those 4 groups, right? That's another way that we can write our null hypothesis. You will see sometimes in symbols, you can write your null hypothesis this way. Again, you do not have to give both of these as your null hypothesis. I'm just showing you this in this example here. And so my alternative can be that there is a significant difference in those population mean scores across among the 4 training groups. That means that at least one of those training methods has a population mean test score that is significantly different from the others. All right. Notice how I said that slightly different than what I said once I saw the screen here. All right. Or you can say at least one of those means is different. All right. But in the general sense, no, all the population means are equal. Alternative, at least one of them is not equal. One of them, at least one is different. All right, let's go to JASP to conduct an analysis here. One of the things that I'm going to start doing is I want to make note because I'm not going to be doing it in all of the examples because these videos are just going to get too long. We still want to do some descriptive statistics when we're conducting these analyses, right? And so I know the first part of our course, we talked about the different types of numbers, tables, and graphs that we can make to describe what we see in our sample. Whenever you're doing a research study, you always want to give your descriptive statistics. So remember that stuff. I'm going to go to JASP just as a reminder. I'm going to open up JASP. Let's make sure this is recording. Yeah. All right. I'm going to go to my computer. I'm in the weeks. I'm going to go browse. And I got my Way ANOVA lecture data. I'm going to open that. This is what our data looks like, right? We have group. We have 10 people in group A, 10 people in group B, 10 people in group C, and the last 10 in group D, right? And then the score on that firefighter test is in this second column here. We hadn't done this in a while, but you can't always use this descriptives menu here. Go to descriptive stats, and you can get some descriptive statistics, right? I'm going to look at the test score, but now I'm going to use the split menu because I know I have 4 groups here. Notice I have 10 individuals in each of those groups. I know the mean of each group. Oh, if I look here in this data set here, one group is much higher than this group here. That's some evidence in the sample, at least, that we have differences in group means. But notice here we have these standard deviations, and they get a little into our variance, our measures of variability there. But this will be a good little table to include. Now, I might take out this missing here since I don't have any missing values, but that's some good information. I really like when I'm looking at Way ANOVAs, using the box plots because we'll be able to see the entire distributions across those groups and be able to compare them, right? So I went to customizable plots here. I clicked on the box plot, and this is my box plot here. And so I can kind of see, yeah, these things overlap here. This is just sample data, right? But this one has a box that's almost completely above this box plot here, right? And the box part of this is above this box here, and there's a little overlap there, right? So this group is at least much different than these others. So there's evidence already that I'm seeing in my data that we have some differences in, we might see a significant result. There's some evidence that we're probably going to reject. All right. Even though that's the case, we still go through with the full process of running a Way ANOVA. All right. So I copied those in the next part of your notes. What I'm going to do next is I'm going to check the assumptions. And so although I have this, what I'm going to do is, yep, that's what I tried to do one time before. I'm going to go to this ANOVA menu. This should be already a part of your JASP. If you don't see this ANOVA menu, you can go over here to this plus sign, and maybe since I already have it here, if you don't have it, you may want to go over there. Since I already have mine here, I think it's a standard there. And if you don't see it, please let me know. But I'm going to go here to ANOVA, and under the classical analysis, I'm going to go to ANOVA. Now, when I want to do any of my assumption checks, right? We already, based off of how our data is made, we're going to assume that our data are independent. So we only want to test the normality and the homogeneity of variance, right? Well, when I do this, I want to put my quantitative variable. My quantitative variable is the test score. That is our dependent variable. Remember, I put DV when I said that. And then my grouping variable, or my factor, I'm going to put it in the box that says fixed factor, right? And so now that I have this here, I can also get my descriptive statistics. If I click on descriptives here, you'll see it gives me my groups, the sample size, mean, standard deviation, standard error, and coefficient of variation. All right. So if you didn't want to go to that other menu, you could have done that here. But let's go to this section here that says assumption checks. If I go there, I have two options here. I can get my homogeneity test. That's to let me do Levine's test for the equality of variances. Notice here, my p-value is 0.445. Notice also that this uses an F statistic. It has 2 degrees of freedom, so DF1 and DF2. And this is my p-value for the test for equality of variances, Levine's test. Remember, if it's not significant, then we can use our regular old ANOVA. So since this is not significant, I'm going to use our regular ANOVA, all right? If this were less than 0.05, I would uncheck this and I would check Welch. That's our alternative when we have unequal variances. All right, so that's that checked out. I'm going to do a QQ plot of residuals. All right, so I'm going to check that. And if I see a somewhat linear pattern or most of the points are close to that line, that is evidence that our data are from a normal distribution, right? Or that our normality assumption is satisfied. So here, our normality assumption is satisfied. If our normality assumption was not satisfied, meaning we saw some kind of curvature going on and not a linear pattern or whatnot, then we would have to use non-parametric statistical test. And there's a menu here in JASP to run a non-parametric test. All right. That's going to be a little beyond what we're going to be required to do in this course since it's an abbreviated semester. But that is there as an option if you have issues with normality. So both of our assumptions are satisfied in this example. And so we know that we can use our one-way ANOVA. So what I'm going to do here is I'm going to scroll up. And we have our ANOVA results here. Notice here, this is my ANOVA information. Now, I want to show you here, this is our ANOVA table. It has my between group variable, so my factor listed here. Notice in my data set, I had group A, B, C, and D. Those are our training methods. All the information about between group variability is given on this first row here in these first 4 columns. And then I have within group information. It's going to be in this second row across those first 4 columns. All right. Now, our F statistic is given here. And remember I said that our F statistic was our mean square between divided by our mean square within. This value here is our mean square between, and this value here is our mean square within. If I do this 1236.3 divided by the 101.728, that should equal approximately 12.153. That value is much bigger than 1. That's evidence that we have a much larger between group variability compared to within group variability, which we can see here. I also want to show you something else. This between these two mean squares are nothing more than the sum of squares divided by the degrees of freedom. So if I took this sum of squares here, 3708.9, and divided it by 3, I'd get this 1236.3 here. And if I took this 3662.2 divided by that degrees of freedom 36, I get that 101.728. So this chart kind of shows us how we're building up to get our F statistic here. So that means sum of squares between divided by the degrees of freedom between, which is 3. Remember, it's number of groups minus the number 1. So 4 groups, A, B, C, D, minus 1 is 3. If I do divide those two, I get that. This sum of squares within divided by its degrees of freedom, n minus 4, right? Or total observation, which is 40, minus the number of groups, which is 4. 40 minus 4 is 36, right? So this stuff is working right. It is what I'm expecting here. But these formulas are very complicated, which is kind of what we've skipped over. But just know that that's the between group sum of squares and the within group sum of squares. In any account, this is our F statistic and this is our p-value. P is less than 0.01. All right. And so if I go back to my notes, I have my ANOVA table here. Since our p-value is less than 0.001, I know that I'm going to reject my null hypothesis, and I can say that there is sufficient evidence at the 0.05 significance level to conclude that at least one training method has a significantly different population mean test score compared to the others. All right, we know that at least one of those is different. We don't know which one. And so what we're going to do in the next video is talk about how we know or how we can determine which mean is significantly different, or if multiple means are significantly different from one another. We'll see you in the next video.